Hello everyone, I'm Lara from eProsima, and today I will host this Artificial Intelligence Integration Working Group. As a recap, on the last AI working group, Rajavendra Selvan from the University of Copenhagen were here and talking about the carbon footprint of the deep learning. And today, my colleague at eProsima, Raúl Sánchez, is here with me. Hello, Raúl.
Hello.
And he will talk about computational effort distribution in ROS2 in the AI integration platform. So, ready?
Yeah. Okay, so I will present my screen.
Perfect.
Okay, perfect. So yeah, as Lara already said, I'm going to talk a little bit about AI integration, integrating platform, and also I will present a use case on which this specific platform for machine learning distribution is going to apply. So the agenda for the presentation is first talking a little bit about AI integrating platform, where does the integrating platform comes from, which is from an European Union project called Alma. Then I will talk about the distributed stacking with AI integrating platform. I briefly show you a use case on how this platform is developed and also how can you use this platform to develop your own environments of distributed machine learning applications. And the third point is how the AI integrating platform can be applied to any other scenarios. So going straight to the first point, the AI integrating platform comes from the Alma Project, and the Alma Project has the mission to provide a new machine learning paradigm known as Algebraic machine learning, which is focused on to be easily understandable by any user. So we are trying to eliminate this black box phenomenon of current deep neural networks in which you keep you lost track of what the neural network is learning. And here on AML, you will have an engine on which you will be able to visualize how the engine is learning continuously. It can be easily integrated with the AML integrating platform, which at the end is just an extension of the AI integrating platform tool. And here at eProsima, we ensure long-term maintenance for the AML environments. Also, just to mention here that there are several companies behind this Alma project, and just highlighting the FKI, for example, which is a research institute very known here in Europe, which focus on machine learning and artificial intelligence. So the algebraic machine learning has several main features, what I briefly describe here. First is less sensitive to statistical features of training data, as it uses algebraic model, complex algebraic models. Then you can combine unstructured data with formal specification of human knowledge. You can give the AML engine a data set of data, as you already do with neural networks. And also you can give some specification and some functionalities to the AML engine in order to restrict how the engine is going to learn. Then it provides a higher mathematical transparency than the current statistical algorithms. And one of the main features that we are taking advantage here with the AI integrating platform is that AML is easily parallelizable, in which you can have distributed deployments of AML engines, all of them learning from different data sets, and also all of them focus on the same problem. And after all the training, you can gather all the models that you have created and combine them, just merging the output model and creating a greater one. And the last one is it's human recognizable training, so you can keep track of how the AML engine is training and all the steps that it's going to take to the final model. Some of the main use cases that we've been covering here in the Alma project and AML already applies is for classification of human motion, in which we cover a human with some sensor and we can predict the motion of the human being. Then interaction with gesture keyboards, with a smart keyboard on the user's phones. Also, we've been focusing with the Carlos III University, another university here located here at Spain, on robot control and path planning. And finally, we are working on how to embed world models and also human ethical actions on AML and AML models. So these are the main use cases that we are working right now on. And yeah, that's everything regarding AML. Now I will move on to the AI integrating platform and how we are taking advantage of this collaborative learning of AML technology. So here's the overview of the AI integrating platform, in which we have several nodes deployed here in our architecture. The green ones are the AML nodes, where the actual computation is happening. Then we have some red nodes which act as an agent to communicate the final AML nodes in order to provide the communication mechanisms to give the communication between one AML node, between another AML node located in another region or even another local area network. And then on the cloud, we have the discovery nodes in which we create a network where every node that we deployed on our infrastructure is going to be connected. So thanks to this AI integrating platform network, we can deploy an environment in which every AML node can be connected. So you can deploy different engines working together on the same or even different data sets, collaborating on the same problem, and after that, just merging everything together, connecting everything thanks to the AI integrating platform. So some of the main features and capabilities of the AI IP is that you can free the edge of training. You can deploy your actual computation to the cloud and then just connect the edge to the cloud easily with the AI integrating platform and just moving models or even data around between the edge and the cloud node. Then it provides parallel training. You can have multiple nodes deployed on your network working collaboratively. It works on real-time environments in which, for example, you are collecting data on the edge and then you want to move that data to the cloud, perform some training, and after that, after the training has already finished, deploy the specific model that you have on the cloud to the different edge nodes. So on the design procedure and the deployment process, you can have the up-to-date model into your edge devices. Then one of the main features here is that all the data is private, because underneath the AI integrating platform, we are using DDS, and more specifically, we are using FastDDS implementation, the FastDDS implementation that we are developing here at eProsima, and all the secure functionalities that we have already deployed and we have already implemented on FastDDS can be covered here. Then it provides the collaborative framework from different nodes working together and talking to each other, and then also it's machine learning model independent. So you can work with any kind of model. Of course, this is mostly focused on AML technology, but for sure, as I will explain later on the demonstrator, you can work with TensorFlow, neural networks, random forest algorithms, and so many more technologies, even though you are not focusing on AML. So that's the introduction here of the AI integrating platform. And the second step is to explain you how we are going to use the AI integrating platform in a common use case, in a distributed stacking use case of machine learning, and how we are going to deploy the different nodes in order to perform a workload distribution in which we will have one main node orchestrating all the network, and then different computing nodes in which the actual computation is going to be performed and where we are going to train the final models. So first, I will cover a little bit about ensemble learning, and there are a lot of techniques regarding the ensemble learning paradigms. The first one that I will cover here is the debugging technique, in which you have a data set and then you can divide that data set in different smaller data sets, and all those smaller data sets are going to be used to train a classifier. So at the end, you will have your original data set divided into, here, for example, you have 3 different or many classifiers, and each of those parts of the original data set are going to be used to train your classifier. And at the end, you will have the bagging technique, in which you will ensemble all the classifiers, all the different weak classifiers into a higher one, which will be used in order to perform the final inference. So this is the first technique, the debugging technique. Then, for example, this is an example of how to use debugging techniques for random forest, in which you will have the data set and 3 different decision trees. All of them will perform a result, and at the end, you will have the final result, which is the combination of the majority voting and also averaging between the results of the 3 different decision trees. So this is just an example of how bagging is used and what bagging in the sense of ensemble learning it's used right now. Then moving on to the next ensemble learning technique, I will be covering the boosting technique, in which here you will have the original data set, and all that data set is going to be used to train your first classifier, which is a weak classifier. Then right after that, you will use the same classifier to classify the original data set, and the positive samples and the positive classification will be given a higher weight, and the classified false data will be given a lower weight. All this weighted data will be fed into a second classifier, performing the same technique as the first one, and at the end you will have 3, 4 different n classifiers, and all of them combined will be created the final ensemble classifier. So this is the boosting technique, in which, yeah, as I said before, original data is going to be used along all the way. And at the end, which is the technique that I will focus here on this demo, is the stacking technique, in which you will have the data set, and the same data set is going to be used to fit different models. So at this point, for example, in this example, you have 4 different models, which can be different from each other, and you will use the same data set to fit each of those one. At the end, you will have a model stack, which is the combination of the 4 models, and you can use this model stack to create a meta learner. And this meta learner will be the final model that you will use to perform your inferences. So this is all the techniques covered in the ensemble learning technologies, and for now, all of those techniques can perform workload parallelization. So you can parallelize all the models working together. But the main problem here is that, for example, for scikit-learn, all of those parallelization can be done in concurrent processes or even concurrent threads, but everything will be kept on the same machine. That this is something that we want to avoid, and we want to extend with the AI integrating platform. Also, for work parallelization, you have some DL frameworks like distributed training with TensorFlow, serving models, also from TensorFlow, PyTorch distributed architectures. And the main issue with all those frameworks is that all of those are framework specific. With the AML integrating platform, you can use any of those frameworks within the AI integrating platform, and all of them are supported. So coming from the drawbacks of current implementation of all these frameworks, the thing that we propose here is to use the AI integrating platform, which is a multi-purpose framework agnostic. So it can be used for any machine learning scenario and development ecosystem. You can use scikit-learn, TensorFlow, even PyTorch within the same architecture and within the same distributed ecosystem. Also, the AI integrating platform is thought to be used using C++ and Python APIs. You can program on C++ or even Python. It's thought to be distributed across different local area networks and wide area networks using common transport protocols as UDP, TCP, and also even TLS over TCP. It is implemented and also designed for efficient data routing, and also it has DDS communication underneath. Thanks to the internal DDS communication, we can achieve internal process, data sharing, or even some memory communication if you are deploying different nodes on the same machine, and every communication will be done straightforward without going to the transport layer. And as it has DDS communication as the communication layer, you can seamlessly integrate the AI integrating platform with your ROS2 stack. So you can communicate your ROS2 networks which actually uses DDS with the nodes of the AI integrating platform. So just coming back to the distributed staking application that I'm going to show you here. As I said before, we have our data set. We will be fed it to 4 different models, and then we create at the end the meta learner. For this specific problem, we will be using the iris dataset, in which we are going to classify the different iris species, and this dataset has four different features. I think maybe some of you already know about this dataset, as this is the most common dataset used in scikit frameworks. And that's why we wanted to use a mostly known dataset. And also this one is very simple, for just to show here how the AI integrating platform works with any kind of problem and for any kind of data. So what we do here is first to train. Let me check here. Yeah. So if we were doing this on a local area scenario without the AI integrating platform, what we were doing is to train the stack classifier on top of 6 base estimators. So here we are going to use 6 different estimators: the random forest classifier, the k-neighbors classifier, the Gaussian process classifier, MLP, AdaBoost, and Gaussian NB. So those are the 6 base estimators that we are going to use for this use case. And at the end, we will be stacking all those estimators into the final stacking classifier. So this is if we were doing this locally without the AI integrating platform. But as we are want to do this parallelize into different machines and into deploy everything into a distributed network, we are going to deploy this specific architecture. So this is the architecture that we are going to follow for this specific use case. In this architecture, we can show different things here, different nodes. those nodes are the main node on the left side, which is the asynchronous main node, which is the orchestrator of our network, and then we have different computing nodes. So the main node will give some orders to the computing nodes, and then the computing node will perform all the training and giving back the final model already trained. So as I said, we will have 6 different estimators here. Here are only represented three of the computing nodes, and this architecture is up to you. So in order to deploy this architecture, you can use as many computing nodes as you want. For example, in case you only have 3 machines, you can use just 3 computing nodes deployed on those 3 different machines, and then the asynchronous main node, which is the orchestrator, will give the orders to the different computing nodes to perform the model training. So once we have seen the main architecture of the AI integrating platform and how this architecture applies to this specific scenario, the first thing to show here is how we are going to distribute the data. So for this demo, all the computing nodes have the final data set. We are not distributing data set between different nodes, which is something that can be easily done with the AI integrating platform. So at the end, you can have the main node with all the data set, and you can send this data set to the different computing node. But this is not something that we are covering on this use case. Here, we want to show just how the models are deployed on different computing nodes and how the model are trained in those computing nodes and giving back to the orchestrator or to the main node. So every node here has the original data set. So once we have the data set distributed between the different computing nodes, the first thing that we are going to deploy here is the main node. So using the AIIP API, we are creating one node, which is the asynchronous main node, in which we have to provide the name of the node in order to be able to check the status of the node on the network, and then the action that this node has to be performed when the solution coming from the computing nodes reaches the orchestrator. And also this solution can be implemented also using the API of the AI integrating platform. In this specific use case, we are using the custom solution listener, which is implemented as follows. So here on our custom solution listener, which inherits from solution listener, which is already implemented on the AI integrating platform, we are creating the function here, solution receive. And this solution receive is the thing that the main node is going to be performing every time that a solution reaches from the computing node to the main node. So here is just printing that the main node received the solution of some task from any computing node. Then we have to distribute the training across the different worker nodes. So what we are doing here is telling the main node how to distribute all the work between the different computing nodes. So for every estimator that we have, for every estimator, which are 6 different estimators covering here, we are going to send a request job to different main node, to the computing nodes deployed. So the main node at the end doesn't know which computing node is sending the job. The only thing that the main node has to know is if the computing node is available or not to receive a job, and send the job to that specific computing node. And that is done on the line node request job solution. And here we're creating the job data type in order to send this specific job, which at the end on our use case is telling the computing node which estimator has to be covered. Once we've configured the main node, we are moving forward to the computing node. Here we are defining the computing node using the API of the AI integrating platform. Then we register the process job callback. Here we are telling the computing node how to process the jobs that are coming from the main node. And here we stated that every time that a job reaches the computing node, it has to perform the computing routine, which at the end is just to train the model with the given estimator and with a given original dataset. At the end, once the training is done, the computing node will send back a solution here, which contains the model and the base estimator to the main node. So the main node at the end will have every model already trained from on the computing nodes. Here is the train function on every computing node. So here, just to say that every computing node has the same code. At the end, it has the same original data and the same code. The only thing that they have to check is the job that the main node is sending to each of them. So, for example, the main node sends one of the computing node that it has to compute the estimator RF. So now the computing node knows that it has to train the random forest classifier. At the end, once we have all the computing nodes done, so every computing node has already finished to train the model, the main node receives all the solutions and it goes to the merging phase in which it will merge predictors and train the final classifier. So what I'm stating here is that based on the solution from the computing nodes, the main node just has to concatenate all the predictor received from any computing node. It doesn't know which computing node has actually computed the actual data, and this is done for each of the base estimators. At the end, it will feed the final stacking classifier using all the received data. So that's everything regarding the demo here. So what we have been seeing in this specific demo is how you can deploy a orchestrator node, how you can deploy a computing node, and how the main node is going to distribute all the jobs and all the work between different computing nodes. And all the computing nodes can behave on their own until they get a job from the main node to which they are connected. So that's everything regarding the demo. Now we can move forward to the third point, which is the AI integrating platform applied to any other scenario. So, for example, we can think of a deployment in which we are communicating different nodes across the internet. So thanks to the agent node, we can deploy different main nodes in different locations in a distributed environment, in different local networks, and all those agent nodes will communicate between each other and will communicate those main nodes to the other computing nodes, which can be located into another local area network. So this is an example of how the AI IP can be deployed using the agent nodes on a communication across the internet. And everything that I've been covered here, it's been developed on GitHub. All the demonstrator that I've been showing here, it's already stated here. For now, this repository is not public, but we will be open public very soon, as soon as we have this the first stable release of the AML integrating platform or the AI integrating platform. We will be able to release this repository containing all the demonstrator and also the demonstrator that I've been showing you in this presentation. And the demos that we are covered in this repository are the scikit-learn demo that I've been already talking about. Another demo with TensorFlow, how to distribute inferences across the AI integrating platform, deploying different models on different nodes, and depending on the availability of those nodes, you can target each of those in order to perform the inference on the edge node. Also, we have some demos with Darknet, and of course with algebraic machine learning. So what I want to state here is that the AI IP is framework agnostic, so you can use this integrating platform for any kind of machine learning technology, covering from the novel technology of algebraic machine learning to scikit-learn, as I showed you before, TensorFlow, or even Darknet. Here are some other scenarios that we already covered in our demos, in which, for example, you have a ROS2 robot with one node of the AI integrating platform integrated into the robot, which will be the edge of the communication. And on the cloud, for example, you can have a training server. So the ROS2 robot is just gathering images, sending all those images to the integrating platform deployed on the cloud. And then after the computation is done, you can move back to the ROS2 robot the model already trained. This can be done with a collaborative training cluster with different AI integrating platform nodes, and also you can cover any other scenario, for example, with a robot swarm, which connects to different servers on different clouds. And yes, that's everything from here. I don't know if everything was very clear. Maybe I went very fast over everything, but
I think
thank you.
we have problem with the sound, and I think that Raúl Sánchez-Mateos
I cannot hear you very well, Lara.
Okay, so
I cannot hear you. I mean, we can
okay,
hear
going
you,
to
but
finish,
it's a lot of noise.
Vivian,
It's like a lot of
can you
echo.
say something? I think there is a lot of sound. So thank you very much for everyone for attending, and see you next month.
Okay, there is a lot of echo, Lara. We cannot understand you very well. But just in any case, anyone has a question?
I have a few questions,
Sure.
if I can proceed. If we go back to this slide number 7, yeah, I will wait. Yeah, this one. We have, yeah.
Lara.
In the example you show with the scikit-learn,
Yeah.
You show that the stacking method with different algorithms. That means that these algorithms will live in one of these green box. Is that correct?
Yes. Yeah, those algorithms will live on the green box. So, for example, you can have the example that I'm covering here, that I've been covering on the demo, is the independent cluster example, in which you have the green boxes, and all of them are AML-IP nodes. So you can have one green box for the main node, another green box for the computing node, and another green box for another computing node.
Ah, okay. So, I
So
understand.
the example that I've been covering, it's for an independent cluster.
Okay, so
Because everything is covered on the same local area network, different
Yeah.
machines, but the same local area network.
Yeah, but the node that orchestrates everything, the main node, I think it's called.
Yeah.
It could be a green one. I mean, it doesn't mean that it should be an orange one, because from this picture in my head, it was like an orange will orchestrate everything.
Yeah. The orange node or the orange red node are the nodes used for communication, just for communicating one cluster to another cluster.
Okay.
So, for example, with this specific architecture, if we are covering from cluster 1 to cluster number 3, we can have a deployment in which you have on cluster number 3 the main node, which is the green one. Then you will have an agent node, which is the red one, and this agent node is going to be used to communicate to another agent node of cluster 1. And then on the cluster 1, you can have computational nodes or computing nodes, and you can have here 5 computing nodes on a different local area network, and you can communicate everything across the internet. So you can have your machine deployed on your network, then just having a main node, and on the cloud you can have computing nodes, for example, and you can communicate everything using these intermediate agent nodes. But at the end, the actual computing nodes and the main node are the green ones.
So once the green ones on the cluster 1 computes the algorithm, for instance, I don't know, some random forest or whatever algorithm, they send back the results through this cloud to the cluster 3. So this main node on the green in the cluster 3 will, it will average or will do something with this result.
Yeah, it will perform all the stacking process.
And this, how the data is integrated is something that it should be implemented in one callback function, or is that correct? I saw in another slide there was some callback implementation, but I didn't understand if this is for integrating results or for doing what.
Yeah, the callback functions are defined so you can tell the node what to do when it receives a job. So, for example, if you are deploying a computing node, the callback function states what the actual computation function of the computing node. And on the main node, the callback function is going to define what to do every time that a main node receives a solution from the computing nodes. So, for example, if I go to the slide in which we have the callback functions, let me check here on the computing node. Yeah, for example, here on the computing node. What we are doing here is to define the process job callback function for a specific computing node. So every time that a job reaches this computing node, it's going to perform this function.
Okay. So this is the code that it will be repeated in all of the nodes.
Yeah.
And if I want at some point, if I want to add some new algorithm, I should redeploy everything. I should change the code on all of the nodes, or how can be done?
You mean if you want to add an algorithm to every main node? I mean, to every computing node?
No. I just want a new node, which I mean, I come back with a new algorithm for this assembly method, and I have a new algorithm for, I don't know. I just discovered that the clustering algorithm works well for some type of problems, but I want to keep the other algorithms. So I just want to deploy a new node with this new algorithm. But as far as I understand, all the nodes share the same code base, so they share the same code. So how can I perform this?
Yeah, so you can deploy another extra computing node just with this algorithm, and also you can create a different channel to communicate the main node with a computing node. So every main node and every computing node, it's communicated using a topic. I mean, in DDS, everything goes through a topic, so all of them share the same topic. So they know that they have to communicate between each other. So you can create another computing node. For example, if you don't want to redeploy everything, you can deploy another computing node. And on the main node, tell that you want to communicate to this different computing node just for this specific task. In that sense, you won't have to redeploy everything on all the existing nodes.
Yeah, because I am thinking that the let's say quotes old nodes won't be aware of the new algorithm, and they won't know how to gather this information. I think I don't know. Okay, thanks.
Yeah, so it's just a matter of creating a new channel between the extra computing node that you are deploying and the main node that you already have deployed.
Okay, and when you say that the method is framework agnostic, it means that either I can deploy nodes with different algorithms in different framework. For instance, something in PyTorch, something in scikit-learn, and something in AML, and then a main node will be able to combine the result from these three different frameworks. Is that correct?
No, what I'm saying here is that you can deploy within the computing function of the computing node you can use any algorithm as internally you are telling the computing node what to do. What you cannot do is to you cannot think of the main node as something predefined. You have to tell the main node also what to do here. So for example, for this specific scenario in which we are using stacking ensemble learning, we already know on the main node which algorithms we are using, and we are applying a specific machine learning method here. So at the end, you only can combine the learners that actually support stacking. Yeah, that actually support stacking. So you cannot combine deep neural networks with AML and at the end think of everything combined on the main node. So you can have, for example, different models deployed on different nodes using TensorFlow or using scikit-learn or using AML and perform some inferences on those nodes. But that's what I'm referring to the framework agnostic, that the part on which you can deploy any kind of node using any kind of framework as TensorFlow or AML, but at the end you will need to know what you are doing, because this is just something for distributed machine learning. So everything that you can do locally, and you can distribute or parallelize into different processes or different threads. Here, with the AI integrating platform, you will be able to do it with a actually distributed architecture with different nodes on different machines.
Okay.
But at the end, you cannot combine frameworks between its.
No. Okay, it's clear for me. Thank you, Raúl.
Thank you, David.
Okay, so anything else? Okay, so thank you very much, Raúl, for the talk. And for the rest of the attendees, thank you very much for being here, and I hope to see you next working group next month. So thank you and bye.
Thank you.
Thank you. Bye-bye.